Hey folks, welcome back. In this video we're going to go over question 4 from the 2021 SQA Advanced Higher Physics exam paper. So let's get started. Question 4 says a space probe is travelling through the region of space known as the Kuiper Belt. The Kuiper Belt lies beyond the orbit of Neptune and contains a large number of small asteroids. As the probe passes through the Kuiper Belt, it travels close to two asteroids. Both asteroids can be approximated as spherical masses. This is shown in figure 4a. So there's the probe and there's the two asteroids of different masses. A part 1 says state what is meant by the term gravitational field strength, and there's one mark available here. Well, we can say gravitational field strength is the gravitational force acting on a unit mass, or you could say on 1 kilogram of mass. And notice how we've got gravitational force underlined here. That means you need to state gravitational force here in order to get the mark. Part 2 says on figure 4b, sketch the gravitational field lines in the region between the asteroids. Gravitational effects from other objects can be ignored. Well, because we've got two different masses here, the gravitational field lines are not going to be symmetrical. They're going to be skewed towards one side so that the point where the gravitational forces cancel out is not directly in the middle between the two masses. So you'd want to sketch something like this, where you're getting one mark for the shape of the field and the direction of the field lines, where the direction of the arrows are going towards the two masses, and you get a mark for showing the skew towards the smaller mass. So the point where the gravitational fields will cancel out would be skewed towards the smaller mass. So at this point here, which is not directly in the middle of the two masses. And for the shape itself, notice how we've got this repulsion between the two masses. It's also worth noting that the field lines must touch the edge of each mass, and that the field lines do not cross. A part 3 says the probe must reach point P. Two possible paths to this point are shown in figure 4c. So the probe can either take path A here or path B round here. It then says state whether the energy required to move the probe to point P via path A will be more than, equal to or less than the energy required to move the probe to point P via path B. Justify your answer, and you'll see there's two marks available here. Well, we could say the energy required is equal to, since the energy required to move mass between 2 points in a gravitational field is independent of the path taken. And another way of thinking about this is that a gravitational field is what we call a conservative field, where the work done in moving mass from one point to another is independent of the path taken. So that means that the energy needed to move along path A will be the same as the energy needed to move along path B. Part B says as the probe travels further from Earth, its onboard clock becomes increasingly desynchronized from clocks on Earth. State whether the clock on board the probe runs faster or slower than clocks on Earth. You must justify your answer, and there's two marks available here. Well, it's important to remember the rule here that clocks run slower in a stronger gravitational field. So we can think about the opposite of that to answer this question, and we can say the clock on the probe runs faster as it is in a weaker gravitational field. Lastly, part C says another asteroid in the Kuiper Belt is at a distance of 49.8 AU from the Sun. Calculate the minimum velocity for this asteroid to escape the gravitational field of the Sun, and there's 4 marks available here. Well, writing down what we know from the question, we're trying to find the escape velocity. We know the universal constant of gravitation, g, is 6.67 times 10 to the minus 11 meters cubed per kilogram per second squared from the datasheet. We know the mass of the Sun, m, from the datasheet is 2.0 times 10 to the 30 kilograms. We're told that the distance r is 49.8 astronomical units, but remember to use that in a calculation, we need to convert it into meters. So we have that 1 AU is 1.5 times 10 to the 11 meters from the datasheet. So doing 49.8 times 1.5 times 10 to the 11 in your calculator will give you an answer of 7.47 times 10 to the 12 meters. Writing down our equation for escape velocity, we have v escape equals the square root of 2gm over r. Substituting in the numbers gives the square root of 2 times 6.67 times 10 to the minus 11 times 2.0 times 10 to the 30 divided by 7.47 times 10 to the 12. And if you put that into your calculator, you should get an answer of 6.0 times 10 to the 3 meters per second. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.